Hello, statistics and pre-calculus. Welcome to your first video on 12.2, geometric sequences. So like last time with the arithmetic sequences, we're going to first do an overview video, then do a video where I work through some problems, hopefully alongside you guys. So in our last videos, we talked about arithmetic sequences, which are sequences like 2, 4, 6, 8, where each number is the previous number plus or minus some constant number. So in that example I just said, we're adding 2 each time, so our constant number, which we said was the common difference, is 2, and then we have an arithmetic sequence when we add 2 to each new number, right? So geometric sequence is kind of similar, but instead of having a common difference where we're adding or subtracting to get our next number, we're actually going to have a common ratio, which we will be adding or multiplying with to get the next number in the sequence. So geometric sequences are kind of going to be our intro into exponentials in general. So exponential growth, exponential decay, these are probably words you have heard thrown out a lot. And this class we're really going to dig into what they actually mean, and that actually starts with geometric sequences. So I wanted to give you guys an example of something in the real world that follows a geometric sequence pattern. So as you guys may know, I'm a polymer scientist by trade. And before I came to HB, I was working at Case in polymer science research, so I actually made polymers from scratch, so I was a chemist. One of the polymers I made were dendrimers, which are these really cool, perfectly symmetrical and spherical balls of polymers, right? And the way we make them is through this convergent exponential growth process. So what does that mean? So what happens is we would take a core, so it has some molecule that has arms, right? So in this case, we have a molecule that has 3 arms, right? And what we did was that each step, we basically went generation by generation, and we added more arms to the arms already there. So in this particular example, this group took a 3-arm core, and then they had a monomer with 2 arms on it, right? So to get from the core to generation 1, they took 3 arms, and they added 2 arms to each of the 3 arms. That means in our generation 1, we have 6 arms. You can probably see where this is going, right? In our next step, we went from 6 arms to 12 arms by once again adding this 2-arm guy to each of our now 6 arms. So that's generation 2. We have 12 arms here. Generation 3, you would get 24 arms as we add 2 arms to each of our now 12 peripheral groups, and so on and so forth. So you ultimately get this really cool structure that has lots of awesome properties, but whose arms basically follow a geometric sequence pattern, and I'm going to actually show you how that's true. So we've already said we have this ratio, right? And we've decided that we're going to call it a common ratio. It's going to be signified by R. So in that example we went from 3 arms to 6 arms to 12 arms to 24. We were able to look at this and say that means our common ratio is 2, right? We multiplied 3 by 2 to get 6, 6 by 2 to get 12, 12 by 2 to get 24, and so on. So with our explicit formula, we would then say g of n equals 3 times 2 to the n minus 1, and ignore the second one. This is not correct. So if you remember PEMDAS, exponents come before multiplication. We can't do those in one step together. So you would actually just leave it like this. 3, which is our g of 1, our first term in the sequence, times 2, which is our common ratio r, raised to the n minus 1 power, right? So then that would tell us if we wanted to find the 70th term in the sequence or the 70th generation of dendrimer arms, we would say g of 70 equals 3 times 2 raised to the 70 minus 1, 69th power. Awesome. So the other way we can write it again is a recursive formula. So remember that while the explicit formula is maybe more easy to understand, the recursive formula is more similar to how we think. So what we did when we were looking at those arms, we would look at the previous one and we would say that has 6, this new one has 12. We took the previous one 6, we multiplied by 2 to get 12, right? So that's what the recursive formula does with math. It tells you first you have to write what the first term is. So g of 1 equals 3. And then you say every subsequent term afterwards is going to equal 2 times the previous term. So g of 4 equals 2 times g of 3. G of 2 equals 2 times g of 1. So g of 2 equals 2 times 3 equals 6, right? G of 120 equals 2 times g of 119. So the difference here is that this is more like how we think. This one will let us find any specific term, because remember with this one we have to know the previous. Alrighty, hope that was a good intro. Next we're going to run through a bunch of examples, and then if you still need some work, you can work on the worksheets on your own.